One of my patrons on Patreon asked about writing your own simple DOS games on FreeDOS. So I wanted to do a video about at least getting your own start on writing a DOS game. Now, in days past, there was this game on DOS that was basically about two gorillas tossing a banana back and forth to each other, an exploding banana. You know, you blow up the other gorilla a certain number of times, then you win. It's a great way for a couple of kids to entertain themselves for, let's say, an hour at a time. It's basically a simple trajectory game, and that's a very simple game that you might write on DOS. So let's write our own version of that on FreeDOS using the OpenWatcom C compiler. Now, I don't have anything in here yet, so let's go ahead and start up a new file, and we're going to use the Fed editor, and that's the folding editor. You can install that on FreeDOS 1.3. I've done some color customizations on that, and you can see the other video about that. But it basically is the editor I like to use when I do programming on DOS. So Fed, and then we'll do this as banana .c. Now I'm going to just sort of at the beginning add some stuff that I need to use later on. So include standard io.h, and that's going to be a useful include if we need to print anything back to the user, and I'm going to do that. I also need to do include con.io, and that'll allow me to do things like, you know, grab a key from the keyboard, you know, useful if it's like press a key to continue, things like that. I may be running in graphics mode for this, so I need to include graph.h. And for what we're doing now, that's a good starting point. We'll add to that later as we add more to our program, but let's start by writing a function that draws a banana on screen. And so let's do a function here called, so it's a void function, and we'll call it banana. Because we're not being very clever with our naming. And what arguments do I want to have in this argument list? Well, I want to have an ability to erase maybe a banana that's already been drawn to the screen. And so I should probably start by adding a variable called int draw, and that'll tell me whether or not I should draw a banana to the screen or just draw a regular blank square. And where do I want to draw this banana? So I need to say int x for that banana and int y for that banana. Those are the screen coordinates to drawing the banana. And then I might want to rotate this banana as the banana goes around on screen. I'm not going to do that right away, but let's just add a variable if we want to do that. Int rot for rotation, and that will tell us the banana's rotation. But we're not going to use that right away, but just be aware. Now let's go ahead and start by erasing a square that we can draw a banana on. So we're going to set a color, and this is an OpenWatcom function, and this will set a graphics color for us. And I want to set this to a background color of 1, and that should be blue, right? And then I want to draw a rectangle, and I'm going to do it with the OpenWatcom function rectangle. And the first argument to that tells the rectangle function if it should just draw a border of the rectangle or if it should fill the interior of the rectangle, which I want to do. I want to fill the interior of the rectangle, and I use that with the parameter gFillInterior. And then I need to tell it where do I want the rectangle to start, and that's going to be X and Y. And then where should it end? And let's say X plus some size, which we'll define as a parameter up above here in a second. And then Y plus size is where it should end. And before I get lost, let's go up here and define a size. And let's just say size is 100, just so we can see it. We'll make that smaller later on. And so now we've drawn a rectangle that's at this point 100 by 100 on the screen, and it's in blue. And that erases anything that's on screen at that point. So let's go ahead and just down here, and if we're supposed to draw it, so if draw is a, let's say a greater than 0, then you should do these things. And so in here, we're going to draw now a banana. Draw a banana. Now, a simple way that you can draw a banana is actually going to draw a circle, and then you're going to cut away part of the circle with the background color. And so that's what we're going to do. We're going to draw, set the background color, set the color, And we want to do this as color 14. This should be the yellow color, the bright yellow color. It's the color of a banana. And so I want to do an ellipse function because that's the general function in OpenWatcom to draw a circle or an ellipse. And so I'm going to do an ellipse that is going to fill the interior. So I'm going to do G fill interior. And where do I want that to start? Well, I want it to basically be in the same rectangle that I was using before. So X, Y, and then it's going to go to X plus size, and then Y plus size. And now I want to draw another ellipse on top of that. And so I'm going to set the color to be 1. It's going to set the same color as the background. And that'll be blue. And now I'm going to do an ellipse that's going to cover half of the banana. So I'm going to do G fill interior. And let's do it at X and Y. And then let's say this is going to be X plus size by 2. And then that's going to be Y plus size by 2. Now, size is an actual number in here. It's 100, and 2 is, of course, a number. And so when I compile this, 100 by 2 will actually be collapsed by the compiler as 50. But for readability, I like to use the parentheses here. And that just tells us, the human, that that's going to be, X plus 50, Y plus 50. And so there's the end of my ellipse function. So now all I've done here is I've drawn a rectangle that is a background color. And then if I'm supposed to draw the banana, then it draws a circle in yellow. And then it draws another circle, actually an ellipse, on top of that in the background color, so blue, to basically erase half of my my full circle, but it's only going to erase an ellipse. And it turns out, if you do a little bit of experimenting, yeah, it turns out by erasing about half of the original circle, you end up with something that looks kind of like a fat banana. It looks pretty good when it gets into smaller sizes. It's still recognizable as a banana when it's pretty big here, like 100. And so that's all we need to do to draw a banana in this case. So let's go ahead and start our main function. So int main. And I want to, let's go ahead and set the display. And if set video mode, and I want to do this as VRes 16 color. Now I'm doing this as a demo. I happen to know that it's going to work going into, VGA 16 color, but always as a safe programmer, you should always check your return values. And this will return a number greater than 0 if the function succeeds. It will return 0 if it fails. And so if that set video mode function returns 0, then I'm going to say put S cannot set video mode. That's why I needed to have standard IO. And then we're going to return back the operating system with a failure. And now that I've done that, let's go ahead and erase the screen. And we're going to do that by just doing a set color of 1. Now, again, that should be blue. And I'm going to do a rectangle. And let's draw it from, that's going to be G fill interior. Let's do that from the upper left of the screen to the lower right. And the graphics screen always starts from 0, 0. And it's actually 640 minus 1 for the horizontal space, and then 480 minus 1 for the vertical space. I could type in those numbers as 639 and 479, but the compiler will take care of some subtraction for me. So I'm going to do it as 640 minus 1, just so we can all see that that's a reminder that it's going to be starting at 0 instead of starting at 1. So 640 minus 1, and then 480 minus 1. So again, the compiler, when I compile this, it's not going to do that math every time I run the program. The compiler will deal with that optimization when I compile it. And so now that has set a rectangle in blue across the entire screen. And now let's go ahead and draw our banana. So I'm going to call, banana. And so I'm going to run our banana function. Oops, banana. And if you remember, the first one was a function or an argument to say whether or not it should draw the banana. So I'm going to draw the banana with 1. Anything that was non-zero will draw the banana. And then where do I want the this thing to start? And so let's draw on the upper left-hand side, and we'll do it at 10, 10, just so we have, so basically kind of close to the upper left-hand corner. And the rotation doesn't matter in this case. We're not going to use rotation, so we'll give it a 0. Any kind of value here would work. And then I want to wait, and so let's do pause. I haven't written this function yet. We'll just do a pause, and then once that's done, then we're going to take the screen down. Right, so this is done, and then we're going to set video mode of default mode, and then return back the operating system with 0. Before I try to compile this, let's write our pause function real quick. That's just a little placeholder function that I could have done this in line, but I kind of like to have a function for it. So I don't care what number or what value comes back. So we'll do this as a void called pause, and it doesn't have anything as an option. And that's going to just use the getCh function. Now getCh will get a single keystroke from the keyboard. The trick is that if it's an extended key, like for example, I think an arrow key or like the function keys, it's going to return 0, and you have to call getCh one more time to get that extended value. I want to have all that happen at once. And so if getCh is 0, then I'm just going to call getCh one more time. And so I've just taken care of that all in one little function. Basically a little wrapper function. Nice little thing to add there. So I think I've got everything I need to draw just a simple banana on screen. Again, I've erased the screen by drawing a rectangle from the upper left to the lower right, and then I've drawn a banana on it, and then I'm waiting for the user to press a key, and then we close down the screen. So let's go ahead and exit this. And now we're going to do a Watcom compiler and linker, and to keep it from being so chatty, we'll do -q and then banana.c. Oops, I used size incorrectly somewhere, so let's go ahead and edit banana.c. Oh, yeah, there it is. Every time I did it in the second time, it looks like I was using a lowercase. Let's do it over here. Just fix that. There we go. Now let's try it one more time. We'll do Watcom compiler and linker on banana.c. I'm not seeing any errors, and so we can now run banana. And you can see that I've messed up my my banana. This is basically a little moon. So now we've drawn a little moon. Let's draw this as a banana. So fed banana.c. What did I do wrong? I meant to go all the way tall, let's say, with a banana. I need to have one of these X or Y dimensions be the entire width or height. So we'll just do this as Y plus size. And so that's going to cover up the left-hand side of the circle. And now we can Watcom compiler and linker, and we can run banana. There we go. That's the banana I was trying to draw. And so we've now drawn a circle, and then on top of that circle, we have drawn an ellipse. And so that is a simple way that you can draw a banana. Now let's make it into a little game, the start of a little game. Now, to make this a similar kind of game to what I was describing before, you want to prompt the user in some way to enter an angle and let's say a initial power, or you might have some graphical mode for them to select an angle and a power. Let's just hard code something just so we can have something to work with. And so fed banana.c, and I'll leave it as an exercise, up to you if you want to make this to a full-sized game. So let's write a function down here that is a trajectory function. Now I want to have it return a value. And so let's make it an integer value here. And that's going to return the x dimension when y goes back to some 0 value. And so we'll say trajectory is our function. We'll just call it traj. And I'm going to do this as double precision variables. And so I'm going to do double the angle that I want to come in. This will be in degrees. And then double the velocity, initial velocity, that's vel0. And then we're going to do the, I know we've done doubles here, but we actually want to do this on plotting on a screen. And so we'll do an integer for an x coordinate on the screen. So that'll be x0. Now, if you followed along on a different programming video we had about Fortran, you saw a similar kind of trajectory program there. We're doing something very similar here. So let's go ahead and say we're going to plot a trajectory of a banana, and we're going to return the x coordinate where y becomes 0, or actually hits 0 or is less than 0. And so we need some variables to track some things for us. And so we'll do some double precision here again as, let's say, the velocity x, that's the x component of our velocity, and velocity y. And I want to have an x coordinate that's actually tracked on the screen, or at least tracked as variables here, since I'm doing everything in double precision. So I want to do a double precision version of the x variable, but just because I like to have it something else, I just happen to call it xx, and we'll do this one as yy. And then I want to do an iteration, number of iterations that we've done. And this is a great way, like if somebody shoots a banana like straight up in the air and it's never going to come back down to earth, or for some other reason we've made an error, I don't want this to keep like going forever and ever and ever. Eventually, after some count of iterations, I want this function to just end. So we're going to use an iteration counter here, and we call it iter. Now, let's assume that the angle is in the range of 0 to 90 degrees, right? And if you take this as a input from a user, you want to do your own verifications. We're going to hard code all this when we call this traj function. So we're just going to make the assumption here that it's 0 to 90, and that the velocity is greater than 0. Right? There's no point in having it sort of just fall to the ground, and we want to make sure that x, y is plottable. We're going to make those assumptions as part of writing this program. Again, your own simple game, you want to do a whole bunch of verifications, but here we'll just do that. Now let's break down our velocity components. And so velocity x is going to be the velocity 0 times the cosine of the angle, and then you need to convert it into radians. And so we've got an angle in degrees because that's easy for humans to look at, but cosine and sine need to take these angles in radian. Now, if you remember your trigonometry, that's going to be the angle times the value pi divided by 180. That's double precision, so I need a 0.0, right? Remember that if you look at, there's 2 pi in a circle, that's 360 degrees. And so for just 180, that's going to be pi. And so if I do angle times pi divided by 180, that will give me an angle in radians. Now I need to have a definition of pi, and we'll put that just right in here. 3.14159265335, and I think it's like 7, but I remember that one off the top of my head, so we'll just put that in there. And so now I've got my velocity x component, and then the velocity y component is going to be velocity 0 times the sine of the angle. And again, we need to put that angle into radians, so angle times pi divided by 180. And then we now need to initialize our x and y coordinates. So we'll say xx is the double cast of the initial x coordinate, and then yy is 0.0. Now I use xx and yy because these are double precision variables, so we'll just double them up. Now we're going to just use a simple trajectory simulation. So simple trajectory simulation. And in this case, we can actually simplify this even further. If you remember your equations of motions, those of you that had physics class, we're gonna, it's we can make some simple assumptions here. So simplify the assumptions even further by saying the delta t is going to be 1, because thus. That means that normally x would be x plus the velocity of x times dt. Right? Over time, that's going to give you, over any dt, delta t, that will give you the next position on something, the initial x value plus the speed times the time, and that gives you a distance. And that means if we're doing this only as dt equals 1, well, that becomes very simple. X, it's just x plus the velocity of x, the x component. That's a very simple assumption if we set dt equal to 1. Again, I can do y is y plus the y component times dt minus 1/2 at squared. And so that's minus 1/2. G is the gravitational constant in this case, dt squared. And if dt is equal to 1, well, actually that becomes pretty easy. Y plus the velocity y component times dt minus 1/2 g. Right, so it becomes a very simple assumption here about how we're writing our functions. Actually, there's one more I want to put in here. That's the velocity y component is normally going to be the velocity of y minus gravity acceleration times the dt. But again, we're going to say dt is 1, and so that makes our math even simpler, and that is the vel y minus g. Why am I going through all this? Because I know there's going to be somebody out there, if I just make these assumptions without it, that's going to not understand this. They're going to complain about the functions being wrong. All I'm doing is I'm just clarifying dt in this case is 1. And actually up here, I don't even have this times dt because dt is 1. So y equals vel y minus 1/2 g. The velocity y is going to change every time because gravity is going to change it, and that's going to be vel y minus g, and then the x coordinate, of course, you see up there, it's x plus vel x. So those are my equations of motion that have been simplified if I say dt equals 1. Now let's go ahead and enter a loop, and so we'll say do, and inside that loop, I'm going to do the next step, do the next iteration step. And so xx is going to be x plus, right? So I can say actually plus equals, that is one more shortening, and that's the velocity of x. And then yy plus equals, you can see up there, it'd be y plus, so that's, I've done the y plus equals. The velocity of y component minus gravity, which is let's just say gravity divided by 2.0, right? That's 1/2 gravity. Let's go up here and we'll just define the gravity. Really, this should be put at the top of the file, but I'm only using it here, so I'm taking a shortcut. Define gravity as being 9.8 meters per second squared. Now, I could make that gravity anything I want because this is really just a simulation, and your users will think it's just fine if you use 10 as a nice round assumption. But we're using double precision variables. We can do 9.8, and that'll be fine. Now let's go ahead and we need to invert the screen coordinates. Why am I doing this? Because when you're plotting graphics, the X and Y is on the upper left-hand side, and certainly X should be on the left side, but Y should be at the bottom. So I want to make sure that we invert the screen coordinates because I want to make sure Y is at the bottom. Y equals 0 should be at the bottom. And so that means that where do I want this to be? We'll say banana, just because now we can draw our banana. We'll adjust the size. We'll make it 10 here in a second. But banana is, yes, we want to draw the banana. And then we're going to convert this to an integer. And there's our X coordinate. And then convert to an integer the calculation of, we'll say 470. We're going to bring it up a little bit from the bottom of the screen. So we'll say 470 minus YY. And so 480 would be, or 479 would be the bottom of the screen. We're going to bring it up a little bit and say 470 minus YY. And then iteration will just increase the iteration. That's a simple way to do your rotation, but I guess we don't need to have rotation here. We can just do 0. Before I get lost, let's first jump up to the top here, and we'll change our size to 10. Because I want this banana to not be 100 anymore. I want it to just be a small banana of 10. And so that has now inverted the screen coordinates so that way 0 is at the bottom of the screen. It's actually at about 470 pixels at the bottom. And then I can do a delay, so that way I kind of have a little bit of a something to see on screen. So we're going to do a delay of some wait time. How much do I want to wait? Let's put this in 200 milliseconds. And that, by the way, is defined up here in include i86.h. That's where we get the delay function. And my math functions, like sine and cosine, they're in math.h. That's cosine and sine functions. So jumping back down here, so now what I've done is I've now iterated my x and my y. But what I haven't done, I just now realized, I haven't actually adjusted the y velocity. So we'll say velocity y is going to be minus equals. Remember up there we had velocity y minus gravity, and so we'll say gravity. There we go. Because again, that was the assumption that dt is 0, which we can do here. And then I've done that do loop, and I need to give it an ending. So I need to say while the iteration, and so we'll take plus plus iter, as long as that is less than, let's say, 100, and I want to make sure that y is greater than 0.0. And that should be a loop that just watches a banana move across the screen in an arc affected by gravity. And when I'm done with that, I can now return the integer cast of xx. And so that's what I need to do there. And now I've done a simple trajectory. And now let's make sure it works. So let's go down here to our main function. And we've drawn our banana. We'll keep that up on screen, I guess. We'll draw a trajectory here. So we'll say trajectory. And remember what that was. That was the angle. And so let's do this at, let's say 55 degrees. It's a little bit more than sort of halfway. So it'll be 55.0. And then I need to give it the initial velocity. And we'll say that's going to be 88. And then we need to give it the X and the Y. I'm sorry, the initial X. And so what's the initial X? We'll give it, let's say 10. Was it? Trajectory was going to be an integer, so it was going to be just 10, not 10.0. And that is my trajectory. And then when it's done, it will prompt the user, or at least it'll just wait for the user to press a key, and then it'll exit the program. Let's see if I've done this right. Let's go ahead and exit our command here. We'll do WCL. We'll do -Q, so that way all the regular stuff that gets printed doesn't get shown up on screen. Banana.c. Wow, I've got something wrong in there. So on line 38 looks like is where things go wrong. So let's do fed banana.c and jump down to line, what was it, 38? And oh, because I don't need to have a semicolon up there. That's certainly one thing that went wrong. Yes, that was exactly what went wrong, because it was inserting the value of pi, which is defined up there, but then it also had a semicolon at the end. It's like having pi with a semicolon here, and that broke the compile. So I don't want to have a semicolon there, which is why I removed it up here at the end of the define statement. Let's go ahead and quit out of that and see if anything else pops up as an error. And parameter count does not agree with the previous definition. So trajectory was I've done something wrong. Let's double check this here on line 95. So what did I do wrong? I forgot to put in a comma. So right here at the end of my velocity, I need to have a comma. That should be okay, because I should just have 3 things coming in. Yep, I got 3 things coming into the directory function. So that should be my last debugging. Now we should compile. Everything looks good. And then banana. And there we go. We've now drawn a banana scooting across the screen. The upper left-hand one is just the one that we hard-coded in there. And so now that's drawn a banana that just scooted across the screen and eventually came down to rest off-screen somewhere. And if I just hit space, you can just see that exit the program. Let's edit that real quick here. Banana.c. And let's change the hard-coded value. So it's no longer doing 55. We'll just make it do, let's say, 66. And let's go ahead and recompile that. And there it comes back down, and it hits the ground, and then we're done. So that is a simple way that you might start a game to play sort of a little toss the banana game. Now, in another video, I will show you how you can do some optimization, including making this banana rotate, but I think that's probably enough for right now. So I'm going to go ahead and stop there. Before I go, I want to thank everybody who supports me on Patreon. You really do make this channel happen. So thank you very much for your support. Some of you are sponsoring me at a higher level, and I thank you again here for that. So thank you very much. Visit our website at FreeDOS.org, join us on Facebook, follow us on Twitter, and consider supporting me on Patreon. Thank you.